Well, thank you very much for the kind introduction, and thank you very much for inviting us to present on Surrey satellite technology. It's a real privilege to be here, and it's really nice to be here in person, having done so many online talks in the past. It's nice to actually be here. I'm going to be talking about the work that we're doing, and I'd like to acknowledge the fact that, particularly when we're talking about HydroGNSS, there's quite a team that's been involved contributing towards it, and you can see some of the contributors, organizations down the bottom, scientists across Europe, and also European Space Agency and the colleagues in Surrey Satellite Technology Limited. So I will be talking about how we are misusing sat-nav signals in order to take measurements about the Earth and the climate. So I'll come on to that in due course. So about Surrey Satellite Technology Limited, I think a number of you will know about it. It's a company that was spun off from the University of Surrey in 1985. It's based in Guildford in Surrey in the United Kingdom. And it's now owned by Airbus, is part of Airbus, Defence and Space Company. And when I started my PhD at the University of Surrey, embedded with the SSTL back in the early 90s, you could probably count the number of companies and organizations that built satellites in the United Kingdom on one hand. And there weren't many other people around the world building satellites either. Obviously a number in the United States, but not that many, and not many around the world. Now, if you look at the scene, there are hundreds and hundreds of organizations that are building satellites, ranging from universities building CubeSats to startup companies to larger companies building satellites, and of course, to some very well-known billionaires who put up hundreds of satellites. So we like to think that we help pave the way for this revolution in small satellites, in particular in SSTL. Where are we now? Well, we are a space mission prime. We build small satellites and constellations. We're a manufacturer and operator, and we offer on-the-job training, and we're a supplier to governments and commercial operators. We are vertically integrated, so we tend to build most things ourselves, and that gives us the intellectual property that we can then build up a training regime to provide training for customers, and we're often the first choice for commercial companies that want to put up satellites. Here are some of the satellites that we've built and launched in the past 5 years. So it's something like 31 satellites and 12 launches. So Galileo, there's 10 payloads that we provided. We've actually built 34 payloads for the Galileo navigation system. We built a satellite for Kazakhstan. Carbonite 2 is a technology demonstrator that demonstrated video from space. ELSA-D was supporting astroscale with space clear-up. And Formosat 7 was 6 satellites we built for Taiwan and for the US that were measuring the weather using GNSS radio occultation. That's another story. And Dot 1 is a little technology demonstration. LEO Phase 1 was a frequency filing satellite. And then we have the 300 S1's 4 1 meter resolution imaging satellites, and Novasar was a radar satellite. OTB-1 was a US deep space clock. We did build an instrument that went on the James Webb Telescope. We built the avionics for 4 remote sensing satellites, Canopus. We built a removed debris demonstrator which fired a harpoon and a net to try and capture a satellite in orbit, and Vesta, and the largest one was Quantum, which was a geostationary satellite. So we have been very busy over the past 5 years with a variety of things from different applications, a lot of remote sensing, but also communications and navigation and technology demonstration. And here's a little window on the satellites that we're building at the moment. So satellite view has been in the news recently because we recently launched one of these satellites. And this is a satellite that monitors the thermal footprint of buildings. So it takes near infrared pictures of buildings, and you can see when the heat is coming off a building. And there is a commercial case there. So there's a company called Satellite View that is commissioned 2 satellites off us, and the hope is to go onto a constellation. We are building a satellite that will be supporting lunar missions. I'll come on to that in a moment. We are building a satellite to support the UK Space Command. It's their first in-orbit asset, it will be. HydroGNSS, I will talk about that shortly. Microsar is a radar to provide a large area maritime surveillance for Norway. We're building well, in fact, we built the satellite for Thailand, video and imaging, and that will be launched next year. And then CarbSAR is a technology demonstrator that's proving an innovative deployable antenna for SAR. So those are the satellites that we're building at the moment. Just a few words about a Lunar Pathfinder. This is a satellite that we're building. It's due to go up and to be launched in 2025. And this provides a data relay for lunar missions and space assets that will be on the moon. So if you want to build a lunar rover and put it on the far side of the moon, then the Lunar Pathfinder could make the communications easier. It provides a communication link back to the Earth. And we're also working on a proposal at the moment for the next phase, which is the Moonlight. It's an ESA mission that will be providing further communications and a navigation service for lunar missions. So we are working on our first lunar mission. Now I'll come on to HydroGNSS. So first of all, this is a Scout mission, and this is a European Space Agency program, which is new. It's recently been introduced. It's like a mini Earth Explorer. For those of you that know the large Earth Explorer missions, this is a mini version. And the aim is to try and tap into new space technologies. And it's to try and show that science can be done with small satellites. And so there is a budget of up to 30 million euros, and it's aiming for 3 years from kickoff to launch. Now, SSTL was one of the 16 bidders that submitted to ESA, and HydroGNSS was one of 2 scouts that was selected to proceed. And so HydroGNSS is now proceeding. It comprises 2 identical satellites, which are using GNSS reflectometry to measure soil moisture and other similar climate variables. We're leading a team of international scientists from Italy, Spain, Finland, Austria, and the UK. And here's a picture from the calibration validation workshop that we held not so long ago in SSTL. It's with our science partners from Europe, ESA customers, and SSTL staff. At this workshop, we were discussing our plans for calibrating the payload and validating the measurements. So taking a step back and looking at what we're trying to do with this mission, we're using SatNav, or sometimes known as, or the Global Navigation Satellite Systems, GNSS, and using it as a radar source. I say misusing it because that's clearly not what it was designed to do. So, but we're trying to see what we can do to make use of this signal. So GPS is the original US system that everyone knows, and Galileo is the European version, most GNSS receivers now being produced will be tracking both GPS Galileo and the Russian GLONASS-1 and probably the Chinese Beidou system as well. There's also regional Japanese, Indian, SBAS, and other sources of signals. And these are, there are over 100 of these satellites transmitting signals from a high altitude. Most of them are in a medium Earth orbit, which is 20 to 24,000 kilometers, and they're transmitting continually. There are some which are higher at the 36,000 kilometers, and each satellite signal is transmitted with about 50 watts of power. So it's not very much power transmitting all these tens of thousands of kilometers. Originally, these signals were for military navigations, for guiding missiles and so on and so forth, but they found plenty of other applications in the civil world as well as military. So they're used for aircraft, for ships, land vehicles, mobile phones that drive your Google Maps, and things like that. I used it on my Voy scooter from the Cambridge station to Churchill College just this evening. And they are L-band microwave signals, somewhere between 1.2 and 1.6 gigahertz, 2 megahertz bandwidth, up to 40 megahertz, some of the widest signals. These aren't really radar signals. You expect much wider bandwidths. You expect wider bandwidths and higher powers. They do provide atomic timing stability. That's what they're for. They're for providing positioning. But how stable is the amplitude? And that was not really quite known. So the reflection of GNSS signals off surfaces is unwanted noise to many people. It's referred to as multipath, and it often degrades accuracy and can sometimes even give you quite the wrong position. When you're driving in the Alps, you get bounces of the signal off the side of the mountain. So extreme reflections have been seen off the ocean by a GPS receiver on a military jet plane in the 1990s. And we know that radar satellites bounce, for example, C-band signals at around 5 gigahertz off the ocean. And we use that to measure wind by the power of the backscatter signals, or nadir reflections, for altimetry. So can we use GNSS? Could we use it as a signal source? We would be using it measure forward scatter because we've got two stations. We've got the transmit station and the receive station. So it's called bistatic radar. And the great thing is you don't need a transmitter. You can just pick up the signals. You just need a modified GNSS receiver to pick up the signals. But the signals are very weak. Can they be picked up from space? And the answer is yes. We had an experiment on UKDMC1 back in 2003, and we did bit grabbing to just capture the data from the RF front end and process it on the ground with a software receiver. And we showed that we could pick up signals reflected off the ocean from space. And unexpectedly, we picked up signals off many surfaces, not just calm ocean. We picked them up off calm ocean, off rough ocean, off ice, and off land. And this was a big surprise to many people. So we went on to develop an instrument that not only picked up these signals, but actually processed them on board. And so after UKDMC, we had a satellite called TechDemosat-1, and we developed an instrument that could generate these measurements on board. And from that, we provided an instrument that enabled the NASA Cygnus mission. That's a hurricane sensing constellation with 8 satellites, and that's been an enormous success. And it's been shown to work in multiple domains for ocean wave sensing, sea ice extent, ice concentration, and land, now addressed by HydroGNSS. So you can see along the bottom the timeline from the early concepts to a demonstration on UKDMC up to today with HydroGNSS. So what are we trying to measure with HydroGNSS? Well, we're trying to measure the water cycle. It's vital as a natural resource to climate, weather, and life on Earth. If you eat food, then you have an interest in soil moisture indirectly. So it's present on or inland in the form of soil moisture, wetlands, rivers, snow, and ice, and vegetation. And people like the World Economic Forum recognize that the water-related issues are amongst the greatest challenges of facing the population for the future, with climate change happening. And so we are, the areas that we're targeting with HydroGNSS are quite important areas, things like soil moisture, the high latitude permafrost, or strictly speaking, the freeze thaw we're measuring, which is a tracer for the permafrost. Biomass is the amount of mass within forests. This is above ground biomass. So this affects carbon stock and biodiversity. And wetlands affects methane emissions, again affecting climate change. We have models that that model the future of the climate and the weather, but they do need measurements to prime them. So Earth system models are used for climate and numerical weather prediction for weather, and they need measurements. Hence, we have these things called essential climate variables. And HydroGNSS is targeting land parameters which are linked to these essential climate variables. So as an organization, Global Climate Observing System, which has specified 54 essential climate variables, and about 60% of them are being addressed by satellite data. And they are measurements which are needed by scientists to model and improve our understanding of the climate. So yeah, soil moisture, biomass, and permafrost are ECVs. So if we can take measurements that contribute towards that, we're contributing towards climate knowledge. Wetland is a primary source of greenhouse gases. We're using reflectometry, which is novel, complementary, and unique, and it addresses a shortage in measurements in L-band in particular, and scientists do like having measurements at different frequencies. It picks out different things from the surface. So here we have an animation of HydroGNSS, which hopefully makes things quite clear about what we're doing. Some of the targets that we're going for: freeze thaw over permafrost, the above ground biomass, the soil moisture, and wetlands and inundation, flooding. We're doing this using reflections from GNSS satellites. So they're at much higher altitude. You can see the Galileo and GPS satellites. They're transmitting continually, as I said, about 50 watts from space. And there's a specular point that glints off the surface, and we are targeting that, and we are looking for the signals, and we create these things called delay Doppler maps that capture the measurements. And it works under all weathers. It penetrates clouds and rain. And it was designed for navigation under all weathers. And so from those delay Doppler maps, we can then process them using special processes to target soil moisture, wetlands, biomass, and the freeze thaw over the permafrost. And we have secondary measurements. We can measure ice extent, and we can also measure the wind speed over oceans as it causes the roughness on the surface. And as the two satellites that are flying in low Earth orbit take measurements in these tracks, they form tracks, and these tracks build up over time. So over a period of, you can see over a period of days, it gradually covers the whole Earth. So that takes global coverage to over 80% every 15 days. So that's HydroGNSS. Now with HydroGNSS, it's not the first reflectometry satellite, but we are adding new things. So the previous satellites, things like TDS and Cygnus, were measuring incoherent delay Doppler maps from GPS single frequency, 1 Hertz, with a single polarization. So this is what we're adding with HydroGNSS. We're adding not only GPS, but Galileo, which increases the coverage. We're adding polarization. We're measuring the opposite polarization as well, not just left, but also right-hand circular polarization. We're adding a coherent complex channel to measure the more coherent reflections that we sometimes see. And we're adding a second frequency, which has got the broader band signals that come down from the GNSS satellites. And with these, we're hoping that we can improve our measurements and we can help separate the different factors. Separating out the soil moisture from roughness vegetation from using these new parameters. So we had to build up the case in order to win a mission. We had to prove that it was feasible, and we had to be new at the same time, which is quite a difficult thing to balance. But somehow we managed to balance this, and this is our evidence for soil moisture. So there's a can see here it's gone drier during the two weeks, and you can see the red patches, and then the next 2 weeks it's gone more. Well, the soil moisture has increased. So that's with SMAP, and then with reflectometry we see exactly the same thing. But you can also see that the tracks, if you look carefully, the tracks are you can see the tracks that have been taken from these reflection tracks. And you can see its higher resolution detail is in there. So we've also been able to compare the sensitivity to other means of measurement, and we're able to look at the resolution. Resolution looks like it's around 2 to 7 kilometers, which is twice as good as other techniques using radiometry. And it improves as the signal becomes coherent over flat surfaces. And HydroGNSS is going to be able to cover the whole globe. And the dual polarization will help detangle the moisture and the roughness effects. So that's soil moisture. And this is inundation wetlands. And the picture on the right is really quite remarkable. This is the measurement from the SMAP passive radiometry instrument, which is used and very much trusted. But you can, it's a measurement of the rivers in the Amazon basin, and you can see the rivers there. But it's not very high resolution. The active element of SMAP, which unfortunately failed not long into the mission, but you can see it's very high resolution. It's actually much higher than reflectometry. But the drawback is that it's covered by all the vegetation. So you can see the rivers, but only the big rivers, which are not masked by the forests. Whereas GNSS reflectometry is finding all the rivers underneath the forests. And the reason why that works is because forward scatter. As the rivers become flat, the signals get stronger. It's the other way around to backscatter. So we are picking out the rivers, whereas most radar loses flat surfaces, has no signal return. We get the strongest return of flat surfaces. That means the signals are strong enough to get through the jungle canopy. And that's why we're able to see measurements under the forest canopy that really nothing much else can measure these things under the forest canopy. And with HydroGNSS, we're adding the coherent channel, which will continue to improve the resolution and maybe allow detection of weaker signals. And potentially it will lead us onto altimetry in the future. And then we've got similar evidence for biomass. Now, this is a different mechanism. We are now measuring how much attenuation happens after reflection. It passes through the vegetation, and then it is attenuated by the vegetation. And the heavy lifting is here being done by artificial intelligence. It's being compared to a database. And we are seeing a good agreement between the database and the measurements from Cygnus here. And this is the sort of one-to-one curve we're looking for, and you can see it's there. Although we do get attenuated by the very heavy, dense forests. And again, HydroGNSS will be able to target the higher latitudes that Cygnus is not able to get at. And in fact, the future ESA biomass mission has some limitations at the higher latitudes, which HydroGNSS will be able to help out with. And then we have the evidence for the freeze thaw. This one is a bit easier in some ways. When you have moist soil that then freezes, the permittivity changes quite dramatically. And so you get a big change. You get a much less reflection. And so we can see this is some data from TDS compared with the SMAP product. And you can see there's a good inverse relationship between the SMAP freeze thaw product and the reflectivity. So the freeze thaw is a product that we can offer with HydroGNSS. People often use a chart like this. It shows the difference, different scales of spatial resolution and temporal resolution. So along the bottom, you've got a different spatial resolution, temporal resolution, ranging from long time to very short time. The spatial resolution is in the other axis. So HydroGNSS sits roughly in the middle, slightly above the middle. And that means it can address these different things. But by adding the coherent channel, we get the HydroGNSS star. If we want increased temporal resolution, then there is a way. You just put up more satellites. Instead of being 15 days, you could then get a repeat every 3 days or even 1 day if you put more satellites up. So that's the way forward. And because they're small satellites, it's practical. It can be done. So just putting it head to head against some of the big cousins. So SMOS and SMAP are the big satellites and budgets of hundreds of millions. And SMAP was, as I said, was $1 billion, and it's 1 ton, 6 meter dish. They are heavily used measurements from SMOS and SMAP, but there's no replacement for them. They're past the end of their life. And so they could, in principle, go at any time. So HydroGNSS is helping to fill that gap. It doesn't fill it completely, but it helps provide continuity with the 2 satellites that we're putting up. In the longer term, there is a Copernicus satellite called SIMA. That could be 2028, it could be later. But HydroGNSS, we are aiming to be up at the end of 2024. And our satellites are much smaller. They're not 1 ton, they're 65 kilograms. And we've got a budget for 2 of them for less than 30 million, and that's for including design. So to repeat build could be quite a bit cheaper. I won't go through all this, but this is laying out the specifications for HydroGNSS, really. This is the mission objectives. So it's got the things like the sort of aim behind the mission. It's got the requirements. You can see there are sort of requirements in terms of soil moisture accuracy, inundation, classification accuracy, freeze thaw state, forest biomass, and resolution. We're aiming for 25 kilometers, but with a goal of 1 kilometer. And timeliness, we are going to try and produce the data within 7 days, aiming for a faster service. And we'll cover 80% of the globe in 30 days for 1 satellite, 15 days for 2 satellites. So we've captured these in a mission requirements document, and we are going to try and validate against this document when we're in orbit that show that we've met these objectives. And again, I won't go into detail here. This is showing the sort of spread of the measurements that we're going to be taking. The important thing to note is that the red asterisks indicate what we measured on the previous mission, TechDemoSat-1. And what we're doing is we're adding the green measurements as well with HydroGNSS. So many more measurements. We're adding Galileo, we're adding the opposite polarization, coherent channel, and the dual frequency. So we're adding to the knowledge on reflectometry, we are expecting to be surprised by some of these measurements. We know roughly what they're going to do, but there were some big surprises when we first put up TDS1. We expect some more surprises with HydroGNSS. And some of the work that we've done with our science partners is quite painstaking, is trying to put together enough proof that we've raised the scientific readiness level. This is an important metric that ESA measures. What is the level of our scientific readiness? And there are criteria for that, which you need to show that you've got the error terms, you understand the error terms, the error modeling, you know what causes errors, you've got those under control. And the way to do that is using a simulator, which our science partners in Italy provided, called HSavers, which allowed us to try and model the error terms and try and understand them. And actually, we've used this as an opportunity to develop the data processors, which are going to be using, we're going to use those on the live data that comes down from space. So we're in a good position where we've developed a lot of the processing for when we're in orbit. Okay, this is interesting, looking at some of the error terms and looking at the mechanism by what we're doing. Simplistically speaking, we are trying to measure this reflectivity on the surface. And so we want to know what's the power reflected divided by the incident power. And that's the fundamental measurement. It's quite simplistic, but that's the measurement that we're doing. So in order to do that, we need to measure the reflected signal well. And that is affected by our antenna pattern. It's affected by what the ambient noise is. We want to separate our measurement from the noise, so we have calibration methods on board. We have a calibration switch on board, but we also use ocean targets and Antarctic targets to provide us with what we hope are known references so that we can then calibrate, measure this accurately. The other part of this is we need to know what's transmitted from the GNSS satellite. And that's interesting. That's not really been done by many people before. And so we've spent quite a bit of time thinking about this, and our colleagues in NASA with the Cygnus mission also spent some time. And what we're doing, amongst other things, we're using the direct transmissions in order to map out the power and the patterns of the transmit satellite. So the good thing about this is that it's a direct measurement. There's not a reflecting surface in a way. So we're able to map out the transmit patterns and the power of the satellite. And if you look at pictures on the right, you can see there's a published pattern of a GPS transmit antenna pattern. And below is our recovered pattern. We've recovered that using data from satellites like TDS1, where we actually mapped it out. In order to do this, we need to know the zenith pattern of our own satellite. So there's a few unknowns. We have to map out these things, but you can see that it's getting there. We're getting it down to fractions of a dB in order so that we can measure this reflectivity more accurately. Now, I mentioned antenna noise. Antenna noise is, ideally, you point an antenna at the ground and it's room temperature, but that's not what we see. We see sometimes some things which we didn't expect. When you point an antenna at the surface of the Earth and try and measure what noise there is in the L-band area, you don't see a uniform noise that's the temperature of the air or the Earth's surface. This is what you see. You see strong patches over the ocean. And you see it quieter over the land. And nobody was expecting this. And in fact, the first calibration algorithms for Cygnus, were aiming to use the oceans, in the middle of the ocean, as the quietest area. You've got a quiet equatorial water. That should be nice. There's no radio emissions. Should be nice and quiet. You can use that to calibrate. Turned out that was the worst thing you can do. Why are these signals so strong? Well, we have theories. We don't have proof, but we're pretty sure it's because above the Earth, you've got all the GNSS satellites transmitting continually. And all the satellites are visible, transmitting. You don't have the code separation that you have, or rather there's enough of them that it brings it above the noise. And because the surface of the ocean is nice and flat, especially around the equator, and it's salty, you get these strong reflections. And you've got the geostationary satellites transmitting. Whereas over the land, it tends to absorb it a bit more, particularly where you've got vegetation. So you see this big change of about 4 dB sometimes going from ocean to land. So it is artificial noise. I think you see less noise. We're lucky. Cygnus didn't have the advantage of being able to get at the poles. But if you look at the Antarctic, it's nice and quiet there, the blue being low noise. And so we can use the Antarctic. That will be better behaved than over the oceans. But there's one or two other things that we're seeing as well, which can't be explained by that. And you can see here, for example, off the west coast of America. And I think if you look another day, you won't see it. So I think there's some naval exercises or something is going on. They're deliberately doing things there off the coast. But you do see other things over in this region as well, the Middle East, and that is there all the time. And that gets stronger, and it's been getting stronger recently for obvious reasons. And also in the sort of Ukraine-Russian border, there's some strong signals around here. And nobody's surprised by that. This is GNSS signals after all. It's what you use to steer drones and missiles and so on. So it's part of the geopolitical situation, shall we say. But by using our calibration methods, we can separate these out from our measurements of the reflections. Although if the signals from the ground are strong enough, it will wipe out our measurements. So it is a concern purely from a selfish, our own measurement point of view, but obviously it does give us a window. And if you look on the web, there are other people who are taking measurements of this from space. So we're not the only ones, and there are some public charts like this on the web. So back to the HydroGNSS mission, and we're building the payload, we're building the satellite, we're also building the ground segment. And the mission operation center, the payload data ground segment is located in Guildford. We're downloading data via Svalbard so that we get good passes. We can have as many as 12 passes a day, although we're only using 3 or so per day. And we have our Guildford ground station as a backup. And for those of you not familiar with remote sensing data, it tends to be dealt with in levels. So for example, level 0 is the data that's produced on the satellite. Level 1 is the first observable. In our case, that's the reflectivity off the surface. And we try and calibrate that reflectivity. And then from that reflectivity, our partners have processes that generate the level 2, which is where you start recognizing the measurements as soil moisture or freeze thaw. And then from level 2, you move to level 3, where it's gridded and mapped, so that you actually have something that can be used, a map of data. And we will be providing the data via a website, as we did for TDS. So the data will be free and open according to ESA's guidelines. Yes, we have our partners providing the processors. And yes, we will provide registration that those that want to access the data. In terms of the satellite itself, the platform is 65 kilograms, microsatellite. It's 5-year life. It's got 3-axis attitude stabilized. We need to know the pointing quite well so that we can map out our antenna pattern. We have xenon propulsion for orbit phasing, collision avoidance, and at the end of the mission, passivating and lowering the orbit. We have an X-band downlink, so we have plenty of data downlink capacity, more than we need really with the X-band. We are using a ride share on Vega C into 550 kilometer 10 a.m., 10 p.m. sun synchronous orbit. It's scheduled for the end of 2024 next year, but we're still trying to firm up with Vega that launch slot. Both satellites will be launched together, and then they'll be phased apart in the orbit by 180 degrees to increase the coverage. We'll commission the satellites from satellite. The satellites are normally going to be tilted about 20 degrees. We pick up more coverage, and we also get more polarization information from the higher incidence angles. I don't talk about the instrument here. I won't go into detail, but it processes the signals from the raw data into these delayed Doppler maps using coherent integration. If there's time and people are interested, I can talk about it later. So recent progress with the mission. So the payload comprises of this electronics unit. It's basically an expanded GNSS receiver with a coprocessor that can pick the signals out from the weak reflections. And we have the low noise amplifiers here down on the right. They are something like 1 dB noise figure, so we try and get the noise figure as low as we can. We have antennas which can provide dual frequency, dual polarization. It was quite a challenge to design this antenna, but now it's there. It's going up on the satellite. And the satellite is looks a bit like this at the moment. There's a few more modules. Within a few weeks, it'll start taking shape into a proper satellite. This is the structural qualification, which is what the satellite will look like near as it approaches launch. Okay, so yes, we are building the first satellite at the moment. Almost all the FM units are in the stack. The second satellite is following closely, so in January, February, the second satellite will start coming together as well. So I'm drawing to an end now with the talk. So just coming back to the topic behind this, the scientists, meteorologists are increasingly using global soil moisture measurements from space. It's something which is highly prized. The accurate weather forecast depends on soil moisture. If you imagine continental masses with warm, damp soil, it affects whether you get tornadoes or not. So these things, if you want to have precise weather forecasting, you do need to take into account the soil moisture. So it contributes towards that. And the soil moisture is needed for flood warning services, for agriculture, for subsidence, permafrost sensing and climate modeling. At the moment, people are using the ESA SMOS and NASA SMAP satellites. They are highly prized. They're using passive L-band radiometry. But both satellites were quite expensive. They don't really have replacements, and they are coming towards the end of their life. So GNSS reflectometry has been recognized as an alternative technology approach. It is a lower cost to achieve the same coverage, and it can achieve higher resolution. It's complementary. It's not measuring quite the same thing that radiometers measure. So there is a need for both. But it's easy to augment GNSS reflectometry because each satellite is only 60 kilos or so. And it's lower cost to achieve the same coverage. The forward scatter is different. It offers a unique ability to sense under vegetation, and it helps towards the essential climate variables. The temporal resolution can be improved if we put up more satellites. So I'm concluding my talk now. I talked a bit about Surrey satellite technology, the small satellite pioneer. We started in 1984 from successful spin-off company, now part of Airbus. We're building satellites for Earth observation, communications, navigation, technology demonstration, and lunar services. A lot of the work that we did in SSTL contributed to the reflectometry becoming a transition from a concept of doubtful feasibility to now something that is well established as low cost but an effective remote sensing technique. HydroGNSS mission is going to be using GNSS reflectometry to target climate variables, including soil moisture, inundation, freeze thaw, biomass, and ocean wind speed. And it observes higher latitude forests and disturbances which are otherwise untargeted. We think that HydroGNSS is going to be a showcase for GNSS reflectometry. It's going to explore new measurements for hydrology, but not only hydrology. It will be valuable for over the ocean and over the ice. And it prepares the way for a constellation of small satellites, sustainable and beneficial for weather, flood, and climate monitoring. And that's the end of my talk. Thank you very much.
Martin, thank you very much. It's a wonderful talk. It was really interesting to just get a sense of what a real mission entails. It's we sort of know what they do at the end, but exactly what was involved is takes it a while. Can I ask my physics question? I'm going to.
Sure, I'll try and answer.
The differentiation you get that allows you to see particularly flat water is the very high dielectric constant of water, even at gigahertz.
I think it may be more to do with the surface shape, actually.
But the differentiation between your moisture content
yes,
would surely depend on.
Yes, I think that's
the low dielectric constant when it's dry.
Yes,
significantly higher when it's
damp.
Okay.
Yes, that's right. But the surface roughness plays a major role. It's the difference between measurements over the ocean, where we always have a ripple or a swell. There's always going to be, well, I say always, occasionally, just occasionally, water becomes very flat in the ocean, but generally you see that in rivers, the ocean, there's always a ripple. And it doesn't take much ripple to add scatter.
Sure.
And so there's a big distinction between when you have scatter, it's diffuse reflection, and then we have flat ocean, flat surface, you suddenly get coherent reflections, and it goes up exponentially when you have a flat surface.
Yep. We do have some online questions, which is good. And to anyone else thinking of putting a question online, it's in the chat, isn't it, Valerie? Sorry, in the Q&A. I got it wrong. Not the chat, the Q&A. But we have from Andrew on the Q&A, how do you confirm the accuracy of your moisture measurements over various surfaces?
That's actually a truly challenging thing to do. And people have been trying to do that with Cygnus. And I think it's a big statistical game, but actually you'd rather you could get it down to individual measurements, and that's very difficult. The best thing that we've got is probably the combination of the simulator and Cygnus. There was a particular target zone in Colorado called the San Luis Valley, where there was a collaboration with University of Michigan and various other people who worked on the Cygnus mission, and our Italian colleagues who tested out their models, and they tried to get it down to the reflectivity. How accurately could you get the reflectivity and make it match with the model?
But you have to do some ground measurements somewhere.
Have to do ground measurements, and there's certain target zones, and it actually isn't easy. And they got down to about an agreement of 2 dBs, which is not very good, to be honest. You know, we would like to try and do a bit better than that.
Great. So if I can turn to questions in the room.
Fascinating and inspiring talk. Space is becoming rather crowded. What are your plans for satellite disposal?
That's a very good question. The space has become very crowded, and since the early days, it's just gone up and up and up. And since in particular, the thing that's really changed things in the past 5 years, perhaps, is these mega constellations. People had always talked about them, but they've only started putting them up. So things like the Starlink constellation from Elon Musk, and the OneWeb constellation, and others. And the sheer number of satellites that put up means that it's forcing people to take this more seriously and apply more rules. And so there are rules coming in. There's already a rule that says at the end of the mission, maybe a rule is too strong a word, but it's how you get, you have to get your license, then you have to comply with this, show best endeavors to meet this requirement. And that is at the end of your mission, you have to make sure that your satellite will deorbit within 25 years. So that's number one. And people have pretty much all complying with that now. You have to passivate your satellite and make sure you deorbit within 25 years. It's getting tighter. I think with the FAA in the US, they're starting to bring in a 5-year rule so that people will try and bring their satellites down within 5 years. There's several companies which are making their business case about collecting wayward satellites and re-entering them. So people are taking this seriously. That's what's happening.
Yeah, thank you very much. Could you say a little bit about how the satellite is powered and what limits its life to the 5 years?
So how the satellite is powered? Yes, it has solar cells. You can see on the picture there the solar panels. And if you ask me which solar cells we're using, I'm not sure I could tell you right now. But we obviously use high spec solar cells, which supply. We also have a battery which stores the energy. The payload takes around 12 watts continuous. So we're not talking about large amounts of power. The other thing that takes a lot of power is when we turn on our X-band transmitter, that drains the power. So we try and limit that.
There's another online question. I think it's a point of a comment on the little red blobs off the coast of California that we saw. This is from Stelios Christodoulou. US Coast Guard Navigation Center should have GPS interruption notices. San Clemente Island off California is often mentioned as a location of approved GPS testing.
That makes sense, yes.
Yeah. So that's good.
Does your satellite rely on a fixed GPS satellite as its source of signals, or can it choose which one it wants to use to get the reflected signal?
That's another good question. This all comes from GPS originally. The first UK DMC, there was only GPS there. TDS, we very much lent on GPS. I think we're getting to the point soon where we can actually start leaning on Galileo as well as GPS. But to be honest, it's very easy to just lean on GPS. I think if GPS started becoming unreliable, the last thing you'd be worried about is a climate monitoring satellite. But yes, we could move over to Galileo.
So we have another online question from Rob Unwin. Have you been able to measure methane releases from areas of melting ice as it bubbles to the water surface?
Yeah, this methane is, we can't measure methane directly with this mechanism. There are satellites that can actually, and there's some interesting ones. There's some satellites that have been launched recently which home in on the methane emissions.
An infrared.
But there are different wavelengths, I think, that home in on the methane. So there are some satellites which do that. What we do though is we measure the overbanking that happens in the Amazon. Nothing else is really measuring that. When the river overbanks, it lays silt out on the bank, and that affects all the climate models, which it is an unaccounted source at the moment. So it's the fact that we're measuring flooding under the Amazon forest cover that allows us to help with the methane knowledge.
Question over to my left.
You go first. Sorry, you are benefiting from forward scattered reflections by doing it bistatically. There will also therefore be considerable forward scattered side lobe and multipath. Are you using the side lobe and multipath, or are you rejecting it very cleverly?
I didn't quite hear all of that. So something about multipath.
Sorry, you are using the forward scattering effect
Yes.
to identify rivers, etc.
Yeah.
But if there's forward scattering, that means you've got forward scattered side lobe and forward scattered multipath. Does that complicate your signal processing, or can you use it?
Yes. Okay. So we are particularly over diffuse surfaces like the ocean. We don't just have a single reflection. When we're over the land, we can simplify it and say there's a reflection point, which is maybe a bit too much of a simplification. But over the ocean, we can't say that. It's over an area. It's a kind of a flux. And we call that the glistening zone. And that's, if you like, it's many, many multipath reflections. It's each facet is like a radar return. And they combine together to make a signal that's not really very coherent. And so we kind of add these together, it's bounded by the code bandwidth, and that decides the size of the footprint and also how much energy returns. So yes, we do take that into account. Is the short answer.
Thank you.
Question to Ella.
Are you using standard microcontrollers, or are you using radiation hardened parts?
A bit of both, perhaps, is the answer. We do make use of smart fusion tools, which are I think they're well known to people for terrestrial applications. We're also using Zincs. They're well known, but there are some special techniques that you can use because they're programmable hardware. You can actually program in registers that are triple modular redundancy. So there are things that you can do, and people like ESA and NASA have done quite a bit of work on assessing how vulnerable. There's different kinds of radiation effects. You get single event effects, which the worst one is a latch up, which could short circuit, and we have to make sure that they don't latch up. Other than that, you get upsets, and upsets you can do something about. You can protect it with redundant coding, and so we use some of those techniques to protect ourselves. We don't eliminate it. Occasionally we do get upsets that we'll have to switch off our instrument and turn it back on again, but the important one is to make sure it's safe from latch ups. It's not going to damage anything.
Great. One last question from the front.
Thanks. Yeah, I noticed you would compare the direct signal from the satellite with the reflected. Does that give you an opportunity to bring height into the equation? I mean, maybe average ocean heights or something.
Yes, actually the direct signal, there's one thing I'll say first before I go into the height. Something we noticed is that over certain parts of the globe, certain GPS satellites change the power by about 1 dB. Suddenly they're much more powerful over the Eurasia, let's say, and then it goes weaker again. And that, of course, is going to muck up all our measurements because we assume one power and then suddenly it jumps. So the reason why we homed in on the direct one, we can map out the antenna patterns, but actually you can use it directly to correct your reflected. You measure that the power has gone up, you can use the direct to correct it. So one of our calibration modes uses that direct correction. Coming back to your other point, can we measure the height? There's a lot of people who would love to see HydroGNSS measuring the altimetry. And I think there are difficulties. Okay, the difficulty over the ocean is that it's not very coherent. And you really need the carrier phase in order to get the sort of centimeter level accuracy. And you haven't got the coherence. You'll get all kinds of speckle and fading and so on, except when it gets really calm. And then suddenly you can measure the height. The other thing is that you need the, but actually when you look at glancing angles, grazing angles, then you're more likely to get coherent signals. So some people have been using grazing reflections in order to measure height. The other thing you need to take into account is the ionosphere, because that adds a delay to your measurement. So if we're able to use the two frequencies, then we can cancel out that ionospheric effect. There's other effects, smaller effects like troposphere. The other thing that you need to do is you need to know your station's location. and not just roughly. You need to know it very accurately, as in down to centimeters. So there are techniques for doing what they call precise orbit determination, POD, using GNSS signals. So we are looking towards that. But there's a lot of little things you need to tick off before you can actually measure the altimetry. But if you can, that's like a holy grail. If you could measure the height of the ocean, you can measure things like El Nino currents, and you can measure the sort of mesoscale eddies, which at the moment are just not being measured. So there's a lot of interest in whether we could do that, but there's a few barriers that would stop us.
Brilliant. So, well, thank you very much. It was just a fascinating talk. It's just so good to get a sense of what's involved in putting a whole project together, and we wish you every success.
All right.
For
Thank
the
you very
launch
much.
next year.
Yeah.
Thank you for making the journey. And
Yeah.
do